Hello everyone. I'm Purba. So today I'll be presenting a recent work of ours that has been published in ABJ. So the title of the presentation is Model Agnostic Cosmological Inference with SDSS IV eBOSS data, where we'll be probing for the simultaneously probing for both the background and the perturbed universe. So we know that the 6-parameter lambda CDM model can provide a reasonable fit to the cosmological evolution, but there are recent tensions and anomalies we are seeing with this 6-parameter configuration, not just the Hubble tension but different other tensions that has been the subject of this meeting. So to address this issue, there are generally two ways. So either we try to look for different systematics in the data sets, or we try to find where the new physics could arise. So to take into account the systematics, so here we are trying to probe a single survey. We take into account a single survey, the SDSS eBOSS, the completed eBOSS plus eBOSS data, which is just a precursor to DESI. And to find out the maximum cosmological information we can find using this data set. To probe for new physics, we try to do a reconstruction in a model independent way directly from data. So this is the basic theoretical framework. We assume a spatially flat FLRW metric to hold true at statistically large scales, and the expansion rate is given by this Hubble function. This is basically the acceleration equation. So when we are trying to model the evolution history of the universe, what we do is we try to assume a kind of parametrization from my right hand side here of the rho, and we try to infer what scale factor or what is basically the Hubble parameter we get from here. Now we are trying to do it in a reverse way because we have data directly of these SDSS observations which measure the radial distances given in the form of this Hubble distance, the transverse to the line of sight, the transverse co-moving distances, and the growth rate of structures from the redshift space distortions. So taking these observations at face value, we try to reconstruct the co-moving distance, the Hubble distance, and the growth rate directly from data. For this, we employ this multi-task regression framework. So because our data consists of observations and auto and cross correlations of these observations in the form of this matrix, we need to map these correlations or auto correlations accurately. So we take into account kernel functions which try to map these features, and also the cross correlation. We do it in a completely Bayesian framework where we try to find out these parameters which we call as the hyperparameters of our model, and finally predict these dm, dh and the f sigma 8 directly from this model. But with the samples we get, we can plot finally 3-dimensional phase portraits of the reconstructed functions at each of these individual redshifts. So these are basically the 6 effective redshifts, the SDSS BO plus RSD data probe, and we can find that we get a volume where shown in blue. So this is basically the volume our reconstruction gives us. So this is basically a force portrait kind of a thing. Now in this phase portrait, if we take the Planck lambda CDM chains and if we try to superimpose it in this figure, so this is shown with this red region, red ellipses. So in the very low redshift, so the plot is shown with the within the 2 sigma confidence level. So in the very low redshifts, we see that up to 0.68, so our results are consistent with Planck lambda CDM for both the background and the perturbation sector. So I am talking about linear perturbation sector. But at 1.48, we see that the 2 volumes do not coincide. So there is some inconsistency we are finding. So data is trying to tell us between what the reconstruction gives versus the Planck lambda CDM predictions. And we also find a similar kind of an inconsistency at the higher redshift 2.33, where the Lyman alpha BO data is there. So now let's interpolate it at as a function of redshifts. So this is basically the profile of dm by rd, this is dh by rd, and this is the f sigma 8. So in the very low redshifts, we see that the Planck lambda reconstruction, which is shown in blue, is consistent with the Planck lambda CDM predictions. But at very high redshifts, at the 2.33 Lyman alpha point, so there is an inconsistency with Planck lambda CDM, which exceeds 2 sigma. A similar nature is also found in the DHRD profile, where we again find more than 2 sigma inconsistency at 2 sigma, which exceeds 2 sigma. For the F sigma 8 data, so we do not have any data point at this high redshift. So the redshift we have, the highest redshift the F sigma 8 data can probe is the 1.48, the quasar data, and we find that there is a more than 2 sigma discrepancy at the F sigma 8 measurement at this redshift. So we can summarize our findings as that these low redshifts, we find good agreement between reconstruction and the lambda CDM predictions. At higher redshifts, there are deviations from Planck lambda CDM. At z equals to 1.48, the Lyman alpha, the quasar data, we find the deviation in the F sigma 8 to be more prominent, but then at the Lyman alpha data, there are anomalies we observe in the DMRD and DHRD. Now, what happens if we try to map each of these volumes to the lambda CDM model? So, assuming lambda CDM is my cosmological model, what happens if I try to fit the model to each of these volumes? These are the plots. So, in this, here is basically the H0 RD, this is sigma 8 and this is my omega m. So, in the first 4 effective redshifts, we see that the correlation between these parameters also remaining same, and the Planck lambda CDM model is coinciding with our reconstructed volumes. But at very close to 1.48, where the quasar data is present, we find that there is a switch in the correlation. So, the direction of this correlation between these 3 parameters changes. At 2.33, we also observe that there is a discrepancy with what our reconstruction gives with Planck lambda CDM. So, we can draw a tension heat map for these cosmological parameters. So, this is for this is a heat map that shows the tension between each of these effective redshifts compared to Planck and also the SDSS lambda CDM predictions. So, we find that for H0 RT, the tension is at around 2 to 2.5 sigma at the Lyman alpha data point. Tension is omega exceeds 3 sigma for the Lyman alpha data point, and for the sigma E, the tension is like 2 to 2.5 sigma tension at 1.48 redshift with the remaining data point. Now, we can draw a whisker plot showing the trend in these parameters. So, because BO data can give us predictions of our H0 RD, we can take RD, we can calibrate RD to the Planck value, and then we can predict H0 from there. Now, interestingly, if you look into the profile of this DHRD, the y-intercept of this figure gives a value, will lead to a value of H0 RD, which is close to 100. That if we inject the RD from the Planck there, we arrive at a H0 that is close to 68, which includes both Planck and shows H0 within the 2 sigma confidence level. So, these are the trends we observe for each of these individual redshifts. So, at z equals to 0.15 to 1.48, so we see that there is an increasing trend in H0. So, H0 is closer to the choose value, and then it closely goes to the Planck value as redshift increases. If we compare this with the for the omega m, we see that the omega m is mostly consistent. Constant value of omega m is mostly consistent within the 1 sigma. However, there is this slightly increase in the mean values of this omega m. For sigma 8, we find that up to 0.7, the sigma 8 value is consistent with Planck lambda CDM within the 1 sigma. However, at 1.48, we find that this is more than 3 sigma tension. Similarly, for the SA, we find there is also a statistical tension at 1.48 redshift for the SA data in our reconstruction case. Now, what happens if we compare this with more future observations? So, SRG rho zeta at DR6 Planck with Planck PR4 and DR6 plus Planck PR4 when cross-correlated with DESI and also the DESI full shape data. So, when we compare the H0 constraints with the DESI full shape data, we observe an oscillating kind of a pattern. So, where the lower redshift values are lying midway between Planck and Schu's, then there is a sudden increase in the value of H0 and then H0 is coming closer to the Planck values. For S8, we observe a similar kind of trend we find in the SDSS data, that at 1.48 we find 1.49 we find that there is again this tension between what Planck predicts and that is which is in more than 2 sigma tension. Also, a similar kind of effective increasing in redshift is found in S8, but in all the 3 cases we find that there is an oscillating pattern. For the DR6 cross-correlated with DESI, we find that there is always an effective increase in these values, and this is more prominent in the parameter S8. For the SRG eRho-zeta, the trends are similar, but this happens at a different kind of a redshift region. So, this kind of a trends in the cosmological parameter shows lambda CDM needs modifications, and this is clearly visible from just one survey, the SDSS BOSS, SDSS eBOSS. Now, with new data, the DESI data coming, so if we look at the DESI data at hand, we can find that at the lower redshifts, we find that there are deviations from Planck lambda CDM as shown in the DESI data. So, and if you plot the equation of state, we observe this kind of a feature in the data set. So, if we try to do our analysis on the DESI full shape data, we will be probing, and if you try to probe this reconstructed phase volumes, so we will find that the correlations to change in between. So, the nature of change in correlation which has been observed here, it will become more prominent at these redshift. So, this framework can be used as a diagnostic tool to test beyond lambda CDM physics at for the next generation future DES 5-year data and also the upcoming Euclid data. And interestingly, this framework can be written as an autonomous system which has been already shown by Charvan et al. And so our framework will provide a model independent template for extracting the maximum cosmological information from a single survey simultaneously for the background and the perturbation sector, which accounts for both autocorrelations and cross correlations between different observables. So, this will offer a robust benchmark for stress testing lambda CDM and which can be useful for future observations. Thank you.
Thanks, Purva, for finishing within time. Questions?
Thanks for nice talk, Purva. Can you please go back to the whisker plots? Yeah. So, if I understand correctly, for say H0, at around z equals 1.49, the error-bursts are relatively large. And for omega matter not, like for z equals 0.15, the error-bursts are large. And consequently, for S8 also, the sigma 8 and S8, they are also large. So how do you interpret this? I mean, like,
okay, so this
is it a good thing or a bad thing? That's the question.
So this is basically the limitation because of the data we have. So for the SDSS, the BOSS plus eBOSS data, so we have DVRD measurements. So we do not have measurements of DMRD, DHRD simultaneously. So there is kind of a loss of information when we try to project it in our phase portrait. The only observation we have directly is for the F sigma. So this causes this increase in the error bars at the lower redshifts. For the 1.48, so the maximum data for the F sigma 8 we have is for the 1.48. After that, our reconstruction basically is unable to account for the features at higher redshifts. So now when we are trying to like model the lambda CDM based on these phase portraited, so at these extreme boundaries we are finding these errors are becoming errors are shooting. So, but with the recent DESI data, because the data is not yet publicly released, but then they have a complete information of all these observables together, so then that can be tested.